The regular.
There's regular, yeah, so the one problem where you fill in the table and you conjecture something, that's a homework problem, and then 1 through 7, they're all computational. They shouldn't take you too long. Thank you. So chapter 10 is on primitive roots. This is really the last section I'm going to really cover here. Next week I'll explain what perfect triangles are, and I'll give you an introduction to Fermat's theorem, and then we'll watch the documentary on them solving Fermat's last theorem. So Euler's theorem tells us that if we have that A and M are relatively prime, then I have this relationship, which you already had to memorize for the past exam. What we can search for is the smallest, this tells you that a power exists, where I can take A and it really turns out to be 1. So you can search for the smallest power K, so that A to the K is really 1, mod M. That smallest such K, that's called the order of A mod M. And if you've had modern, this is the same thing as order from modern algebra. So if you've taken modern algebra, then you know that the order of an element of a group, and you usually talk about Zn as the groups, it turns out to be the smallest K that takes A back to the identity element. So in this case, the identity element is 1. So it's exactly the same definition as order that you get from modern algebra. And if you have a cyclic group, then the order of this A turns out, which generates the group, turns out to be the order of the cyclic group. And that means that's the number of elements in the group. They turn out to be one and the same thing. So if you had modern already, those things should be tying together. They're exactly the same definition. If you haven't had modern, don't freak out. It's just something that you will see because it's a required class. So when you talk about order in that class, it's the same as order in this class. So this is the same. So for example, when in modern algebra, so maybe I think people are taking it next semester anyways. In modern algebra, when we talk about the congruence classes and break up the congruence classes mod 7, we really are putting those congruence classes as a set. And since we're taking the integers and we're putting them into this box, these boxes, we represent that set by taking the integers, the symbol for the integers, which is this Z right here, and then subscripting by 7, indicating that we're modding by 7. And we've done this several times. You'll have, in some textbooks, they'll have actual boxes around the 0, 1, 2, 3, and all the way to 6. In our class, we haven't had boxes. We actually write congruence mod 7. So that, and then we talk about the remainders mod 7. And I told you that you're really boxing up the integers. But that's how they represent it in modern algebra. It turns out that the number 1 can generate that entire set, because if you keep adding 1 over and over and over again, you'll get every element in the set. 1 added 7 times gives you 0, right? Mod 0, I'm at mod 7. So you can get the 0 that comes out in front by just adding 1 7 times. It turns out that you can get the 1 from the 1 because you leave it alone, you'll get it. 1 plus 1 will give you the 2, 1 plus 1 plus 1 will give you the 3, and so forth. So we call this number 1 a generator of that set. And this is all modern algebra. I just wanted to, if you had it, I'm reminding you, if you haven't had it, you'll see it shortly. Not that far away. The order of that set, it's actually the number of elements of the set. So turns out that the order of Z7 is 7 because there's 7 elements in Z7. The order of this number, 1, is also 7, because in 7 times, when you add it, you get 0, and 0 is the identity element of this set. So this is what I mean by order of the element equals the number of elements in the set. They turn out to be the same thing.
So how do you consider?
If I add 1 7 times, 1 to the 7th here is adding. So if I add 1 7 times, I get 0 because I'm modding by 7.
Okay.
Right?
Yes.
And that's the identity element in Z7 with addition. So in modern algebra, you're given a little asterisk at the beginning of the class semester they'll tell you that's a binary operation, and people will confuse that with multiplication. It's not. It's whatever they define it to be. So when you first start modern algebra, that little star that they give you is usually plus. So in this case, star is plus, adding.
With the same question she just asked,
If I take 1 and add it 7 times, I get 7. But the remainder when I divide 7 by 7 is 0, right?
And what's the E?
E means identity element. So maybe it's not a bad idea to write up the definition of a group. How many of you taking modern next semester? I love modern algebra. Love it. You have my number. So I always tell my pre-calc students, if I'm rattling something off the top of my head, beware. It means I've used it and used it and used it. It must be important, and you probably have to memorize it too. So it's not a bad idea to memorize the definition of a group before you even start walking in the class. So a group is a set with a binary operation. Binary operation just means that you can glue 2 elements in the set together by this operation. The operation has to have the property that it's closed. That means that if I stick or glue 2 elements together, that they stay inside the set. So plus is an example of that. If I take 2 elements in Z7 and I glue them together by the plus sign, they still remain in Z7, right? It's not like I got an irrational number or something weird, right, that came out of it. Number 2 is there's got to be what we call an identity element, things that leave things unchanged. So, for example, 0 does that here. If I add 0 to anything, it leaves it unchanged. Number 3 is that every element's got to have another element that reverses it and takes it back to the identity. It's an inverse. Some books, unfortunately, put B is equal to A with a -1 symbol as a caret, and then students start thinking they can divide. Dr. Williams is a lot nicer than I am. I take full points off whenever I see division in a group because you're not dividing. You can't divide in Z7. It doesn't make any sense, right? The inverse of 2. What would the inverse of 2 be? It's the number that you take back to the 0. The inverse of 2 is not 1/2, and it's not going to be -2. That makes no sense here, right? The inverse of 2 is going to be 5 because 5 plus 2 makes 0. So it's not a good notation to have an inverse symbol in algebra. Then the last property is the associative property, that taking the first 2 elements and gluing them together is the same thing as taking the last 2 elements and gluing them together first and then tacking on the first one. So these are the properties of a group, and you'll have to memorize them if you're in modern algebra. And if you had modern algebra, you had to memorize it, I'm pretty sure.
Is this in the book or?
It may not be in the book, but it definitely is on Wikipedia. It's a standard definition of a group. So depending on what book you use, sometimes they put this first property in the definition of binary operation, that it's one of these things that glue things together and doesn't go out of the set. And sometimes they usually the little symbol E stands for identity. And sometimes they, instead of using the B like I did, they call it a to the negative 1 power. So they might use different notation, but this is standard definition, cookie cutter. Who had Williamson for modern algebra? What book did you guys use? Galleon? Okay, I'm using the same one. I'm using the same one for the graduate. Yeah, so he will have it like this. That's a good book. How do you find an order? Well, you're looking for the smallest k such that 3 to the k is 1 mod 8. No, in this one it's multiplication. So when they do this in the modern algebra class, they can switch this to be multiplication, right? But all these properties have to hold. So if you have, for example, the integers, for example, as your g, these properties won't hold under multiplication because every element's got to have an inverse. And you need fractions for that, right? The identity element would be 1. That's the thing that leaves things unchanged when you multiply, right?
But I'm just thinking because before you did 1 to the power 7, you added it. So
Right. So if you haven't had modern algebra, don't worry about it. But you have? then I'm worrying about it. So I'm trying to tie what we're doing in here to your modern algebra class, okay? The examples you have in modern algebra when you begin the class is not things with multiplication, because multiplication usually won't make a group. You have problems with, like, think of the integers. You need fractions to get back to 1. 1 would be the identity, right? So your first examples that you work out with are examples with addition. So that's why I chose this example with the binary operation being addition. Because if I had to come up with something with multiplication, I think I'd have to give you a very specific looking set, right? So that I get around that. It turns out that ZP with 0 taken out of it is going to be a group under multiplication. And I don't know if you remember that. Don't make me sad here. Don't make me sad. You're hurting me. My graduate students love the class. My undergrads love the class too. It's a wonderful topic. It's a beautiful topic. I learned my number theory in that class, but I love number theory too, if you can't tell. But what you're looking for is the smallest integer k by multiplication that gives you back 1. So you just start making a table. Just start. K equals 1, 3 to the 1 power 3. I didn't get there. K equals 2. 3 squared is 9. Mod by 8 is 1. So I found it. The answer is k equals 2. So the order of 3 is 2 because it took me 2 multiplications to get back to 1. So these are computational. You want me to go back?
Yeah. Okay. So when you say the order 3 is 2, because it took you 2 multiplications.
3 squared, right. So I just made a table, and the first power that I found that led me back to 1, that's the order.
Okay.
Right?
Okay.
Right? So 5 and 7 should be easy for you. This should be the easiest test coming up. I'm going to say this into the microphone. That's not true for pre-calculus, in case they accidentally look.
I like
Exam 2 was a bloodbath. Grading exam 2.
Thank you.
It was a very violent exam. You know, maybe why you didn't enjoy the modern algebra is you have these kind of definitions and you have these kind of things like congruence equations all at once. But you going into that class now, you're not going to have that issue because you would have seen these ideas before. Right? You're learning all these things at once. They'll have congruence equations and all that stuff at once. I think you spend a day on congruence equations and all of a sudden you're in groups and it might seem like a blur.
Yeah, I think so.
Dr. Lee thinks so too.
No,
Yeah, you'll not have the problems that she had because you'll have seen a lot of these ideas. You'll know what a congruence class is. You'll know all those ideas before you get there. And you know how to write a proof.
So for the homework, so I'm expressing this 5 to the k congruent to 7 mod 8. And I'm trying
No, 5 to the k, you're mod 8. Find the order of both 5 and then do it also for 7.
1 mod 8.
Mod 8, yeah.
1 mod
with
8.
the
Like
one in the
Not. Yeah, you set them all equal to 1 mod 8. The order's always 1,
okay.
right? It's the minimum k that takes you back to 1.
So 5k congruent to 1 mod 8 and 7k. So
Right.
7 to the k. Okay.